On this first page that I gave you, this is just a nice reference sheet to kind of put together our 2 units in this unit 2. At the beginning of this topic or unit, we started talking about properties of exponents and exponential functions. Then we started talking about logarithms. We covered that last class. We've learned how to convert between exponential and logarithms. This is my log loop. If you maybe want to write that down right here, that might be something helpful. This is what I've called the log loop. That's how we convert back and forth between logarithms and exponential. And then we studied the general shape of logarithms and exponentials. We learned that they are inverses of each other. Again, this is all stuff that's copy-pasted from other sets of notes, so we're not really going over anything on this page. This is just a nice reference for you, so you don't have to look at 3 different sets of notes for all of this information. Okay, so keep this handy. Slide it to the side of your desk. This is just a reference sheet for you. What our goal today is to learn how to solve exponentials and logarithmic functions. There is so many varieties of this type of question that we have lots of different things to look for, and it changes how we attack the problem. So the first page here, you'll notice, has blanks at the top and has some filled in equations already. So what I want you to do is, we're going to pause for a second. I want you to read through the examples that I've already done. You're going to see if you can come up with 4 steps to how to solve this. You're going to write your 4 steps in the 4 steps at the top. Write it in pencil in case you want to change what your 4 steps are when I give them to you at the end. But I want you to look at example 1, part A and B, and example 2, part A and B, and see if you can come up with what the steps are. Write your steps down and then apply it to problem C for both example 1 and example 2. So yes, I have not told you anything, but I've given you perfectly worked out examples here to try to figure it out. So let's take like 5 minutes. Let's see if we can figure out, maybe with our team, what the 4 steps are. Here we go. Let's try it. All right, let's chat. Let's see what we wrote down for our 4 steps. Again, your steps are written in your words, which means they're probably absolutely fine. If you would like to add some more steps to match it with mine, or if your steps are not right, maybe do change it. The first step in solving an equation with either only one logarithm or one exponential is to isolate the base or the logarithm. So base meaning you're isolating the term with a power, with an x as an exponent, or just the logarithm itself, making sure that the logarithm is the only thing on its side of the equation. The second is to convert into the alternate form, meaning you are changing it from an exponential to a logarithm or a logarithm to an exponential. This is where that log loop is going to come in handy. We'll log loop both the exponentials into logarithms and the logarithms into exponentials. Put that in parentheses. Okay, step 3 is kind of a variety show. You're going to solve for the variable. That may require 1, 2, 3 multi-steps, maybe the quadratic formula, maybe just factoring to solve, but generally solving for the variable. And the last step is going to be simplify the exact answer, or round appropriately. So basically giving me my final answer. So a couple things I want to point out to you about these problems as we looked through them. The first few steps were really pretty easy. In part A of number 2, we added 2 to both sides. We took the log loop, so that's base 4 of 9 equal to x. This right here is called an exact answer. So in the question itself, which I did not read out loud, it said write your answers in exact form. If this was on the non-calculator portion of the AP test, we would stop right there. That's what you circle as the answer. We're done. We can't do this next part without a calculator. But if it asks for a decimal approximation, you are going to type log base 4 of 9 into your calculator and then round to 3 decimals. Does that make sense? Okay, so if you get it to x equals something and there's a logarithm involved, that's an exact answer, because most likely, definitely, unless it's a weird example where you get a whole number, you're going to have some decimal approximation. So we'd have to round, we'd lose specificity, we like exact answers better. In number B, we subtracted 5 from both sides, then took the log loop, log base 2 of 21 equal to x plus 3. It required a step of solving to isolate the x. We subtracted 3 from both sides. Now this is going to be important, and I didn't type this in, make sure that you know that this is log base 2 of 21, take a breath, minus 3. Not log base 2 of 21 minus 3. There's a difference. I didn't put the parentheses there, and I'm realizing I probably should have. But that is our exact form answer. X equal to log base 2 of 21 minus 3 is the exact answer. That's what we would type into a calculator on the calculator portion of the test to get, bless you, the decimal approximation. Does that make sense? So depending on what the question asks and what part of the test it's on, you might answer 2 different ways. On your homework tonight, I have given you all of the decimal approximation answers, but I still want to see the exact form and the decimal approximation on your paper, which you have to have the exact form to get the decimal approximation. So it makes sense. In part C, let's make sure we did this one right because I had you try it already. What we would have done is subtract 3 to both sides. That means this is negative 10 equal to negative 4 e to the x. We're going to divide by negative 4 on both sides. It would give me positive 5/2 equal to e to the x. That is all the isolate step because right now the e to the x is by itself. We had to have that happen. If you're like, whoa, where'd the 5/2 come from? 10 divided by 4 reduces to 5 divided by 2, which is 2.5 if you made it a decimal. At this point, we do the log. Yes, sir?
How can you divide?
How come I'm dividing?
Yeah.
Great question. I want to get this e to the x by itself because I want to isolate the term with a power. So I would divide by negative 4 so that the e to the x is straight up by itself.
Is it only for e to the x or anything else you block?
Any base to a power x. Because we're trying to get x by itself, which first we have to get the base by itself so that then we can log loop it. So if there's a number in front of your base and power, you do have to divide by it.
So if you said log instead of e, you still divide?
Correct, because the log would have to be isolated. Yes. So this 10 divided by negative 4, again, that's 5/2 equal to e to the x. Now we log loop it. What is the base here? The base is e. We're going to do log base e of 5/2 equal to x, which some of your spidey senses are going off. Log base e is just like writing natural log of 5/2. Log base e. That's what an exact answer would look like, but if we throw that into a calculator, you would get approximately 0.916. So again, this is your exact answer. Once you type it in a calculator to get a decimal approximation, obviously that is your decimal approximation. How did we do? How do we do on writing our steps? Did we get pretty close? Good. That's great. Now those same steps are going to work if this was a logarithm because these 3 were exponential equations, but the steps are the same for logarithms. Again, we have these nice examples worked out for you. In number A, subtract 4 from both sides, divide by 2 so that I can isolate the logarithm. Once the logarithm is isolated, we loop it. Base is 3, raise it to power 3 of equal to x plus 3. 3 to the third power is 27. Subtract 3 from both sides to isolate for x. And we get an exact answer here. I didn't have to round, so there's no decimal approximation. And it's something I could essentially do in my head without a calculator. As long as you remember your power families. 3 to the third is 27. For part B, we looked through it again. Subtract 2 from both sides. The log is already isolated, so I can just do the log loop there. This is base 5 raised to the second power equal to 2x minus 1. We're solving for x, so I have to add 1 to both sides, then divide by 2. 5 squared is 25. That's how that changed here. So that's 26 divided by 2, which is 13. So voila, we have our exact answer because there was no rounding. I could do that without a calculator. So the one I asked you to try, here's what we should have gotten. First step is to isolate the natural log, which means I need to multiply both sides by 5 so that the denominator of 5 goes away. So natural log of 2 minus x is going to be equal to 5. At this point, the natural log is isolated, so I log loop it. What's the base here? E. So this is going to be e to the 5th power equal to 2 minus x. I need to solve for x, so I'm going to subtract 2 from both sides. But that still leaves me with negative x. So to make this positive x, all you do is switch the signs. I did switch the order at the same time, but basically I divided by a negative, which makes the e to the 5th negative and the minus 2 positive. I just like to see positive numbers in the front. That's my habit, so I just switched their order as well. This right here is your exact answer, because at this point I'd have to have a calculator to be able to calculate the decimal approximation, because e to the 5th power is not something you can do in your head. But if we were to do the decimal approximation for this, you would get approximately negative 146.413. That feels weird. Hold on. Just kidding. That's right. It's negative. That's why it's so big. How did we do on that one? That one was a little bit more challenging because the base e was hidden. And we had to remember that e is a constant, so we're dealing with all numbers here. Cool, great, awesome. Any questions about solving logarithms with only one logarithm or exponent in the problem? Feeling good. Okay, let's go to a different kind of question. On the back page of this, we have equations that are going to involve multiple logarithms. Now, we're going to do the same thing. This time, though, the instructions got a little bit more complicated. The thing is, there are two types of problems on this page. I want you to see if you can at least figure out the one that has been printed on the paper, because I've only shown you examples of one of them. So I want you to figure out what step 1 and step 2 for form 1 is going to be. I've given you 3 and then check on 4. Okay, so same thing we did on the front page. See if you and your team can come up with the steps for numbers 1, form 1, and number 4. That's blank there. And then I want you to try to do C only. Don't go to D yet, but try to do C only. Okay, let's try it again. You're working on these problems. Okay, now you've had a chance to look through them. The first step here, I'm looking for something like the word simplify or condense. You are trying to condense the logarithms into one or few logarithms. You're going to make sure that you're using the log properties from that first page that I gave you in notes today. What is happening with my pencil? There it goes. Using log properties. The first form that you're going to find, and I know this is a little confusing because you don't actually have an example of form 2, is going to be when you have a log with base a of x equal to log with base a of y. What I'm meaning is you have a logarithm on both sides, but all of the logarithms have the same base. The examples that I gave you were this form. After they condensed them, meaning you had a log on one side, you had a log on the other, what did we do with the stuff, the x and the y? With this and with this. What did we do with them after that? I'm thinking like, let me highlight for you so you see what I'm talking about. I'm talking about like this and like this. What did I do with that blue and that green thing? Took away the log. We just set the arguments equal to each other. Since the logarithms have the same base, it's like we can just like get rid of the logs. We've taken out the logs because those logs will be equal if x is equal to y, meaning that you are setting the arguments equal to each other. Now at this point, the solving part, again, is going to have some variety. Maybe a one-step, a two-step, a quadratic equation. Doesn't matter how we solve it, as long as it's appropriate for the problem. You're going to solve for the variable, simplify and round, etc. What is the fourth step here, though? Because last time I had a fourth step being simplify and round, but now that's tucked into step 3. What would be step 4? Check the solution. This is going to be huge. Logarithms have restrictions on domains. So we have to make sure that when we solve, that we're going to check for extraneous solutions. Extraneous looks like the word extra on purpose. It is an extra solution that doesn't actually abide by the original rules of the logarithm. So we take the solutions we get and we plug them back into both arguments to determine that that would make the argument greater than 0. Because remember, a logarithm cannot be less than 0 or equal to 0. So it has to be greater than 0. And it has an important note here. Again, that's just about your properties, because apparently a lot of students forget that you can't just set x and y and z and add them and set them equal to each other. We actually have to condense first. Don't be tempted by that. Okay, let's look at the two examples. We'll come back from form 2 in just a second. I started you off with A, and we did some condensing. So adding becomes multiplying. So this is 3 times x and 3 times 4. That's where 3x plus 12 came from. We distributed there. Yes, did we follow? We set the arguments equal to each other, and then boop, 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 I solve for x. Yes? Okay. Then I went to check my solutions, because I think that x equal to 7 is the solution. So I take that number 7, and I plug it back into each and every argument. Was there anything to plug in for this first argument? No, but 3 is greater than 0, which is good. Check. We technically plugged it in. We just didn't have to plug it in anywhere. Then I take that 7, I plug it in for x here. X plus 4 has to be greater than 0. Well, 7 plus 4 is 11. Is 11 greater than 0? Check. Then I plug it into the last argument. 5 times x minus 2 is 5 times 7 minus 2. That's 35 minus 2. Is 33 greater than 0? If you get all checks, then you can, with confidence, say that that is your solution. If you get a single x mark, you have to throw that solution away. It is not allowed to be an answer if it breaks one of any of the original logarithm arguments. Yes? Okay, we look at example B. Again, I'll slow down on this one because this one's a little bit of a doozy. We start off by condensing. This is not just a simple one distribution. This becomes a double distribution. Do y'all see that? So if I'm adding these two logarithms, that means I have to multiply their arguments together. That makes this a quadratic. Yes? Did we see that? Okay, cool. How do we solve quadratics? GCF potentially. What else? What did I do from this step to this step? Set it equal to 0. Okay, so we're remembering all of our solving rules for quadratics. This is just part of the solve step. We solve a quadratic by setting it equal to 0. What is this called? When you go from this to this? Say it again. Factoring. That's one of the ways to solve a quadratic is factoring. Then we set both factors equal to 0, and boom, boom, I have my two solutions. Now, but we pause because this is a logarithm. I take both of these solutions and I plug it into all 3 arguments. For the first one, we have 5 plus 2, that's 7. 7's bigger than 0. We have 5 minus 3, that's 2. 2 is bigger than 0. And then like 14, I didn't have to plug anything in, but it's greater than 0. We're good. Then I take negative 4 and I plug it in. But negative 4 plus 2 is negative 2. Is that bigger than 0? No. I literally could stop right there, because the moment I get an x on one of these things, we're going to have to throw it away. So we'd say, just kidding, not this one. It's extraneous. If a question asks you for the solution, you say 5 only. But it may also ask you for the extraneous solution, so it's good to know which one is extraneous and which one is an actual solution to the problem. Do we see that? Okay. If you did not actually try letter C yet, I'm going to give you a little bit more time to work through it now that we've worked through the examples and written down some notes. Maybe like 2 or 3 minutes to see how far we can get in this problem in 2-3 minutes. On your marks, get set, go. You got it. Okay, is this one going to be multiplied? No, we actually have to pay attention to the condensed step. Based on the rules we learned last time, when you subtract logarithms, what do you do with their arguments? Divide them. So my first step, and as I walked around the room, everybody skipped writing this part down. And like technically I know you did it in your head to get to the next step, but since we are potentially having this on a free response question and the readers look at your work, we're going to show every step of work. So this should actually say natural log of x plus 1 over 3x minus 5 equal to natural log of 7. I do need to see that step because that's showing me you use the properties of logarithms correctly, and also because most of us did not use the properties of logarithms correctly when we attempted this problem just now. So I want to see that step. Once we get to this step though, this is what most of you did. You're like, well, if they're going to be equal, we can just go ahead and skip to this step. I get it. I need to see that first step so that I know where you decided or why you decided to divide or why you decided to multiply. Yes? Now, the solve part of this problem is a variety show. I could ask you to solve any kind of equation. Part A on this example was just a regular linear equation. Part B was a quadratic. This one's a rational function. The way that you solve a rational function is by multiplying both sides by the denominator, essentially to make the denominator disappear on the left-hand side. 7 times 3 is 21, and 7 times -5 is -35. So I have 21x minus 35. I multiplied and distributed at the same time. Well, now it's a plain literal linear equation, so we can solve. I'll subtract 20x from both sides. Subtract 21 to get -20x and add 1 to the other side to get -36. So I subtract -21x, I subtract 1. I did 2 little moves at the same time. We divide by -20. This is -36 divided by -20. The negatives obviously will cancel out, and this actually reduces to 9/5. But we can't box this answer yet because we have to verify that it is actually okay based on the arguments. So I'm going to take this number 9/5 and I'm going to plug it into each and every argument. We will check and see if 9/5 plus 1 is greater than 0. We will check and see if 3 times 9/5, I didn't write the 1, minus 5 is greater than 0. And then technically you would plug it into 7, but there's nothing to plug it in there. So 7 being greater than 0 is already good. 9/5 plus 1, I know I don't really care what the number is, but is that going to be greater than 0? So if you have a positive number and you add numbers to it, yeah, it's going to be greater than 0. If you care, that's 14/9. 14/9 is greater than 0. We're good. 3 times 9/5, if we're doing the math on that, is 27/5. When you subtract 5, you get 2/5. Is 2/5 greater than 0? Yes, so we're good. We can actually say that x is equal to 9/5. We're good in saying that's the solution. So for most of us, when I was walking around the room and seeing this one, we just overlooked the minus and tried to solve this as a quadratic, which yes, would work if we were solving this as a quadratic, but this one is a rational function. So that solve step can get crazy. Any type of function we studied so far in class is liable to be there in the solve step. You got to keep all of your algebra skills handy. Now, part D is the second form of a logarithm that we can see. There is more than one logarithm present, so it's not exactly like the problems on the front, but it is more like the problems on the front once we get past the first step. Because if I go on part D and I start condensing, again, I have subtraction, so what does that mean for my logarithms? What am I going to do with them? Divide them. So this is natural log of x divided by 3 equal to 2. There is not a logarithm on both sides anymore, so we can't just set them equal to each other. But what does this now look like? Flip your paper to the front side, please. What does it look like now that you're looking at the front side of your paper? Oh, it looks like those kinds of questions where there was only one logarithm present. So we go back to those rules. Those rules said that after it is isolated, you log loop it. This would be e to the second power equal to x divided by 3. I still solve for my variable, which means I'm going to multiply both sides by 3. 3e squared equal to x. That is my exact answer. And then if I beep, type it in a calculator, you would get x approximately equal to 22.167. So I have my exact answer, and I have my approximate answer. Now, if I were to plug this number back into my logarithms to check, the only one I technically have to plug it into is this guy right here. So is 22.167 greater than 0? Yeah, it is. If we had happened to get a negative number, we'd immediately have to throw it away and we'd have no solution at all.
Where do you get the e squared?
A natural logarithm, remember, has a sneaky base of e. So this is written as natural logarithm, but it could also be written as log base e of x over 3. We just don't normally write them like that. We write it with natural log. We need to go back up to the top and write down the steps for this one. because technically it's different than the first form. So the second form you can get when there are multiple logarithms is if it looks like log base A of x equal to some number. I'm just going to use the hashtag sign for number so you know that it's equal to a number. When this happens, you're just going to go back and you're going to log loop it like the front. So you actually follow the front steps, but all you're doing is the log loop steps. So sometimes when you condense multiple logarithms, it'll look like form 1, where we have a logarithm on both sides. And sometimes when you condense it, it will look like a logarithm equal to a number, which is kind of easier. You just loop them and you solve for x. Either way, you check your answers when you start with logarithms, because there are restrictions on the domain of logarithms always. Shall we see another couple problems? Okay, now you can flip it over. On the next page, I still have one more done for you here. So let's look through it and just make sure we know what's going on before you try one. What did I do from what's typed on the page to the first step? I'll zoom in.
Is there no homework?
I haven't passed it out yet. What did I do? What's changed? No. But I like what you're thinking, because you're like, that 3 disappeared, right? So I didn't divide it, though, because not everything got divided by 3. Where did it go? Ah, I heard it. We move any number that's here where? Behind the 2. That would make that 2 to the 3rd power. What is 2 to the 3rd power? 8. Ah, that's where the 8 came from. Don't forget about that property of logarithms. Numbers in front go to become exponents. Okay, cool. After that step, what did I do? So after we got here, how did I get here? Yeah, I use the properties of logarithms that says subtract. We can just divide the arguments. Okay? From this one to this one, what did I do? The logs go away. We set the arguments equal to each other so that the logarithms are equal to each other. Cool. Then I multiplied by 8. This is just the general solve step. So that's 8x plus 56. Subtract 8x from both sides. Divide by -7. I get -8. Cool. Great. Awesome. I think that's the answer. But what happens when you take that solution and you plug it in? It's less than 0, because -8 is not bigger than 0, and -1 is not bigger than 0. The moment you get an x on there, it is an extraneous solution and you'd have to cross it out, which means we're left with nothing. So this particular equation has no solution because we solved it, but the solution was extraneous. It didn't fit the original restrictions of the domains. Make sense? Your turn. You've got example F here. Now this one is very similar to E. I know on the other ones y'all were looking for the front. And I know that it got cut off. Sorry, I forgot to say this. I know the problem got cut off. Somehow it's on the other page at the very, very bottom, right? Sorry. You can transfer it here so it's not just at the bottom of the other side. I'm normally really good at checking my page breaks, but I missed one. So sorry. I'll zoom in so you can see it for me. This is what I want you to work on. My bad. All right, I feel like at this point we're either stuck or we got it, so let's chat. On this problem, again, I noticed that there is a number in front of this logarithm, so if I'm going to start condensing them, I have to move that to the top. Again, that's 2 to the 3rd power. Oh, how nice, I gave you the same problem. So this is log of x plus log of 8 equal to log of 2x minus 7. I see that there's a plus sign in between those logarithms, so when I condense those into 1, that's going to be 8x, because we're going to multiply those. And now the logarithms have the same base, 1 on each side. So I can set the arguments equal to each other. This would be 8x equal to 2x minus 7. Subtract 2x from both sides, and divide by 6. So we should get -7/6 as my solution. However, don't get overzealous and just put a box around that. We do have to check our answers. If you were just to plug -7x into that first logarithm, is -7/6 greater than 0? No way. Which means I already throw it away. I should check the other one just because that's good math habits. She's going to go and then you can go. But we know that the moment it doesn't work in one, it doesn't work in any of them. So my correct solution here is that there is no solution to this logarithmic equation. How are we feeling? Okay, Chris just had a really good question. He just asked me, does all of the answers have to be positive then? What do y'all think? Do all of your solutions have to straight up be positive numbers? Ooh, I heard yes and no. Talk to me. Tell me more.
The x doesn't have to always be positive.
But
the check does.
okay, yes. So the way we would say that is the x doesn't necessarily have to be positive, but as long as when you plug it in to each and every argument, you get a number that is bigger than 0, meaning you got a check mark here. That's okay. So you could have a negative solution as long as when you plug it in, everything's okay. Does that make sense?
Yes.
Okay. Yeah, don't just like start crossing out negative answers because sometimes they are actual solutions. All right, let's make this a little bit harder, shall we? Yeah, we got this. In problem number 4, it's the same kind of question, but I'm asking you in a different way. It says, let f of x equal to natural log of x plus 10 minus natural log of x, and let's g of x equal to natural log of x plus 3. Find all x values where the graph of f and g intersect. What does it mean graphically for things to intersect? They cross, which means they are what to each other? Oh, not necessarily perpendicular. They technically could be. Well, not logarithms. They're not straight lines, but
There's a point.
there's a point where they are, looking for a word that starts with an E. Equal. Okay, cool. So we're trying to see where these two lines are equal. So we're going to set them equal to each other. I would use some small handwriting on this one, by the way. We want to see where f of x would exactly be equal to g of x. This is where the two graphs would intersect. That's what intersecting on a graph means. There is a point that they share because they are equal. So, okay, let's fill that in. That means we're doing natural log of x plus 10 minus natural log of x equal to natural log of x plus 3. Those are the two equations I have. Well, this problem now looks just like it did at the top. What do I do to start solving this? Condense. I condense by making this a division problem, x plus 10 divided by x equal to natural log of x plus 3. Now that the natural logs match, there is 1 on each side and they have the same base, I can take the arguments and set them equal to each other, which means this is x plus 10 divided by x equal to x plus 3. All of those steps we've done before, yes? But when I go to solve this one, we did a rational function earlier. What do I do to start solving this rational function? By the? Cool. When I multiply by the denominator, here's what happens. X times x is x squared. 3 times x is 3x. What kind of equation did we just make? Quadratic. It's a squared term. We have a quadratic polynomial. Man, we started with some logarithms. We ended up with a rational. Now we got a polynomial. Whoa. I love math. Okay, so when we solve a quadratic, we set it equal to 0, which means I'm going to subtract x from both sides. That's positive 2x, and I'm going to subtract 10 from both sides. I always like to go towards the x squared term so that I don't make the x squared negative. That's why I moved it to the right, which is weird. Normally you move it all to the left, but I'm going towards the x squared. All right, let's try to factor this. What you got on factoring? We'd set it up with an x and an x. What are numbers, factors of 10 that add to 2? Oh, I'm so glad I'm seeing confused faces. Does it work at all? Ooh, lean back into your math knowledge. What happens when something's not factorable? How do we solve it? It doesn't have a GCF, a good idea. If it did, we could do that. That is something we can try. It just doesn't work for this problem. Oh, it does have a solution. Guess and check is part of factoring. Thank you so much for attempting to answer my question. Here's what we're going to do. We're going to use the handy dandy quadratic formula, which is x equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Yay! The quadratic formula is back. I'll give you a second to write that down. All right, I'll perform the song for you. It goes to the tune of Pop Goes the Weasel. Singing voice in the morning. It goes like this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is where you clap for me. Thank you. Thank you so much. Yep. Thank you for the pity claps. Okay, so however you remember the quadratic formula, if you remember the story that Ms. Govea taught you, I never learned the story, so I don't know it to help you out. I know it in song. Which is also fun because I love singing, even though I'm not good at it. Let's fill it in though. So when we fill in this formula, we have x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Did I lose anybody on finding those values? Do we know where a, b, and c came from?
No.
So a is in front of the x squared. This is a, 1. 1. 2 is here, that's b. And then c is this number, negative 10.
So the first one's always like the power of x to the power of 9.
If there's a number in front of x squared, that's a. The number in front of x squared is 1. We just don't write 1s in front of coefficients. I know your brains are panicking because I'm making you do a quadratic equation. We haven't done that in a minute, but we start by simplifying the discriminant, which is the stuff underneath the square root. 2 squared is 4. 4 times 1 times negative 10 is negative 40. So that's minus negative 40. So that's plus 40, which means this would be x equal to negative 2 plus or minus the square root 4 minus negative 40. Sorry, 4 plus 40. Is 44, all over 2. What do we do after this? We haven't done a quadratic formula in a while. Can you take the square root of 44? It's not a perfect square, so what do we do? The little tree. Oh, I know. Okay, we can do it in our head. 44 would divide into 4 times 11, yeah? What would 4 divide into? 2 and 2, yeah? Okay, that comes out. So this is actually negative 2 plus or minus 2 square root of 11 over 2. That's doing the tree. We just did the tree in our head. 4 and 11. 4 becomes 2 and 2. Last but not least, all of those 2's are going to cancel out, which is this. It means that this is negative 1 plus or minus square root of 11. Now again, before we get overzealous, we just put a box around it. What do we have to do with both of these numbers? It's a logarithm. What's the last step on solving a logarithm always? Check. Now, of course, plugging that in is kind of weird. So if you would like to, on these problems, change it to a decimal approximation. The first decimal approximation using the plus sign is 5.633. The next decimal approximation using the minus version of this is negative 7.633. One of those is extraneous. Which one? If you were to plug those numbers back into the original functions, which one would make it negative? The negative 7.633. Obviously, because this is just a plain x right here, our values do have to be bigger than 0. So we're going to throw this one away. And our solution is approximately 5.633. The other one is extraneous. Oh my goodness. Okay, before we lose it, hold on, come back. So until we got to this moment with the quadratic formula, did we follow all of these steps? The thing that's going to stump you on these problems is the solve aspect of the argument of the logarithm changes every time. I can't show you every kind of example you're going to see. You've taken 11 to 12 years of math. It could be any of the things that you've learned. in the solve step. Can we try number 5? Yes, you can. I will tell you, you do not have to use the quadratic formula at number 5. So take a deep breath and let's try number 5. You got it. This one's on you. I believe in you. I know you're stressed, but I believe in you. I'm going to put the first few steps on the board just so if you're stuck, you can see where to start, or if you're just anxious, you can check and see if you've done it correctly. But I'm not going to say anything while I do it, by the way. Just listen. Okay, I'm going to get you this far, and then I'm going to let you finish. For some of you were like, that's where I got stuck. It's okay, keep thinking about it. You're right. Yep. Thank you. That better? Okay. All right, let's keep going. So I would subtract 8x and 2 from both sides, which would make this 2x squared minus 3x minus 14 equal to 0. When we factor this, you would use the guess and check method. That's how I like you to factor, which means that this would be 2x minus 7 and x plus 2, which means our two solutions are x equal to positive 7 over 2 and x equal to negative 2, right? Okay, wait, I see confused faces. So yes, what are we looking at the factoring moment? Okay, remember when you're doing the guess and check, you have to make sure that when you do the outsides and the insides, it adds to the negative 3. Where did I get the 7 and the 2 from? Great question. I'm looking for factors of 14. 14 only. Factors of the last number that then adds the middle number when you do the outsides and the insides. So this is 4 and negative 7. 4 plus negative 7 is negative 3. Yes? Then we quickly solve. That's the zero product property. We've been doing that since forever. And we have our two solutions. Yes? No. What do we have to do at the end? Check. If we look back at what we were given, we have 3 different arguments. We have 2x minus 3, we have x plus 4, and we have 8x minus 2. I'm going to give you a second to check all of those. I need to ensure that both of these solutions work in all 3 examples. Sorry, all 3 arguments before I can say that's my final answer. Okay, if we plugged these in, the first one would be 2 times 7 over 2 minus 3. That's 14 over 2 minus 3. That is a positive number. That one works. 7 over 2 plus 4 is a positive number plus a positive number. That's still going to be positive. And then 8 times 7 over 2 is like, what's 56 divided by 2? 28. 28 plus 2 is still a positive number. When we plug in the second one, though, 2 times negative 2 is negative 4. Negative 4 minus 3, is that bigger than 0? No, we got an x here, so even though we get a check mark here, as long as there is one single x, which there actually is 2 x's here, you have to throw this one away. It is extraneous. So the only actual solution we have here is 7 over 2. Or 3.5 if you don't love fractions. So the solve step of these questions, again, is a wild card. It could be anything. You have to be prepared for all types of solvings that we've done since forever. All right, let's check on a couple. We have 2 more topics to go over. One of them very simple, and the other one actually also very simple. We've crossed the hardest things today already off the list. All right, equations with multiple exponential functions. So let's look at this again. I want you to figure out what would go in the 2 blanks by looking at the 2 examples. So take a second, look at these two examples, figure out what I did each time, and see if you can figure out what words would go here in these blanks. All right, what are we thinking here? The first problem looks super simple. What happened? The 2's are gone. The bases just disappear. So if we want the bases to be equal, the exponents have to be equal. We've actually done this idea when we did really basic logarithm stuff and solved the values, like doing the log loop. We set the exponents equal to each other and solve for x. Did I really say 8 divided by 3 is 7 on here? Wow, that's embarrassing. Is that printed on y'all's? It should just stop at 8 divided by 3. I obviously copy pasted this from another page. Oh, embarrassing. Okay. Happens. But what happens on the second one? From the start, did they have the same base? So was I able to just set the exponents equal to each other? What did I do? Specifically, maybe zooming your eyes in from here to here. What did I do? That's exactly what I wanted to hear. We are looking for them to have common bases or the same base. And we're going to use exponent properties to do that. So we're going to work with the, wow, can I spell the word exponent correctly today? Exponent properties. So we use the logarithm properties to solve logarithms. So we use exponent properties to solve exponents. Amazing. So in this problem, number A was super easy because the bases already matched. That's the goal, is to get the bases to match, same base, set the exponents equal to each other, easy solve. For part B, though, the bases did not match when we started. This was an 8, this one was a 2. We have to get them to match. But 8 is in the power family of 2, so we can do that. Now, once I got it to say 2 to the 3rd power, so it had a base of 2, what did I do with this number 3? Right there. Yeah, I essentially distributed it to the others. That's a power of a power, meaning multiply. So if you want to, it is not technically, like, distribution is for multiplication only, but it kind of looks like distribution. So don't tell anybody you're doing distribution, because they'll be like, you're not, because distribution is for multiplying. But you can kind of think of it like that. We're multiplying that exponent to the other exponent. That's a power of a power, multiply. Now the bases match. Yay. We set the exponents equal to each other and we solve. Sound good? Can we apply that to 2 more problems? I'll do one of them with you, and then I'm going to have you do one of them on your own. And yes, I'm leaving the harder one for you. For part C, do they automatically have the same base? No. But do you recognize 9 and 27 are part of the same power family? Which power family? 3. Let's write them with bases of 3. 9 is the same as 3 squared. 27 is the same as 3 cubed. If you recognize these power families, which I've asked you to do multiple times, is have these power families memorized, this is really pretty simple. This is 3 to the 4x equal to 3 to the 3x plus 6. Once the bases match, all we have to do is set the exponents equal to each other. 4x equal to 3x plus 6. Subtract 3x from both sides, that's x equal to 6. And voila, I'm done. Yes? It should say plus 5. Yeah, I do totally have a typo up there. Thank you. This should say plus. It doesn't mess up the problem at all, though. It should still be 11. Thank you. Wow, this page was not great for me. That's 2 typos already on this page. We're going to blame that on Monday, even though today is Tuesday. Okay, part D is for you. This is the last one we're going to do. We'll pick up these notes. We'll finish them next class. It won't keep you from being able to do your homework, which, yes, I have not passed it out to you yet. It's still coming. But I want you to do part D before we go. Yes? Yes. Okay, for part D, did you notice that these are not the same base, but they could be? What are they both the power family of? Wow, everybody saw that. I totally solved it differently on my notes, but let's do power of 2. If I were to write this as 2, this would be 2 to the negative 1 power. Did we get that? Yay, we're finally remembering that rule. This one would be 2 to the 2nd power. Once the bases match, after I do a little bit of distribution here, 5x minus 7 equal to 2 to the 2x. Then we can set the exponents equal to each other and quickly solve for x. We subtract 2x from both sides, and yes, I just ran out of room. We're going to add 7 to both sides at the same time to save some space. Divide by negative 7 on both sides. What does x equal to? Negative 1. Okay, cool. I solved them by putting as power families of 4, which also works. And you get the same thing. Oh, but you avoid using fractions. Oh yeah, this way is way easier than what I did on my key. Okay, cool. We will finish these notes next class. So we'll finish this last little bit. It does not keep you from being able to do your homework by not having these examples, because there are no questions about this on your homework anyways. Sorry we talked the whole time. Told you they were lengthy notes today.